And next, we reach our ultimate definition, which is the diffusion efficiency. So according to the paper by Gonian colleagues, they define the diffusion efficiency as by averaging the reciprocal of the mean first passage time over all node pairs as follows. So this is, you know, the diffusion efficiency here of a graph. So we're just taking the reciprocal of the mean first passage or the average number of hops and normalizing it over all node pairs. Okay? So now, what does this mean? Let's look. So here, let me do this. So this is an important exercise for you guys. Going back to the beginning of our story, we have defined using the shortest graph routing, the E global, okay, which is the inverse of the harmonic mean. You guys remember this formula in the beginning of lecture 5, okay? And in this lecture, we have defined the diffusion-based efficiency, okay? Now, you both know how to compute this. We can use Dijkstra algorithm. Actually, this could be a very nice homework. So here, we want to know how these graphs, you know, like where are they located depending on their topology and structure, where they will be located in this, oops, I cannot move it. Okay, it's okay, I can copy it. Where they will be located in our space, in this space. What do you think? Where should I put these graphs? Think about it, okay? Think about the two measures, their definitions, okay? And then where should these graphs go on the graph, on this plot? So to make it easy for you, I'm gonna divide it up into 4 sections. So this is low, low, low E global, low also E diffusion. And then we have E diffusion low, the other one is high. And then we have, this is high, low, and this is high, high. Okay? Okay, guys, so where should these go? I will give you numbers, okay? So this is number 1, 2, 3, and 4 for these 4 quadrants. 1 minute, think, justify. So ideally, we would have graphs. Well, if you want to improve the efficiency, right? We want to have graphs in this quadrant. So maybe I use a different color. And the purple one. This one is the worst one. Okay, so anyone? So if you look at diffusion, okay, so this graph, if you want to diffuse, because it has a core, so if you're diffusing from the core to any, on average, because you have a core, on average, the average diffusion across this graph, okay? You will see because of the core, you will have like a very good diffusion, okay? Now, as for the length, okay, the global efficiency, if you're using the shortest path length, you know the core is a good hub, right? Like it easily allows to find the shortest path because of the periphery, everything is closed. So I would expect that any information that you want to transfer or communicate from the core to the periphery within this network, it will be very efficiently communicated, okay? So we can put it right here. So this is just, you know, by intuitively, let's say. Now for this one, you can see that for this type of graph, you have like two very dense cores right there. And these dense cores, actually the information might for the diffusion, to diffuse from this one to the other one, to find this optimal path, it might get stuck in these cores. Okay, so you might diffuse along this because of the detours, because what you have. So because of these two cores, you might not be able to really go through this, okay? So to find the shortest path from any node. So the diffusion is very efficient within the core and at the peripheral nodes to the core. But if you have like a very long pathway, you might, if you explore this one, you might easily, you know, go back, be trapped at the core, okay? So the core here might act as a trapping point for the diffusion. So in that case, it has a low diffusion. And also, when you do the global efficiency, you see globally that this is also not, it has a low global efficiency. Now, how do we know that? How can we demonstrate that? So you guys feel free to look at this nice paper, and it has also animations, videos, simulating different graphs. So in this paper, by Goni and collaborators, 2013, they were exploring what they called, this is what they called the morphospace of communication efficiency in complex networks or graphs. So they have discovered by simulating what they called canonical graphs. So they defined graphs with different structures, like for example, star-like graphs right here. And they also defined graphs with highly connected cores. And things like are a bit hybrid, like these forms. They also defined modular graphs with different modules, like here, okay? So they noticed that on this space, when they plotted these graphs, they discovered that there are three big fronts, okay? So the front two, basically this one where you have the most efficient graphs in both measures, okay? It's the star-like nets. Then for the second front, this is a very nice paper, by the way. For the third front, they discovered that, well, you have a high diffusion here using, if you have like a very densely connected core, but because it diffuses, you know, the core nodes can easily diffuse information to other neighboring nodes. However, for this one, still to reach the other nodes, as you go further and it branches out, you have more pathways. It's not just very immediate nodes. So you can see here, both are quite good, right? But then as you add more peripheral nodes, as you know, like you branch out, you go away from the core, you notice that the global efficiency is dropping, okay? Now what we have, until we get to this one, you have a core, but it's like very branched out right there. And then for the first front, where you have the other way around, so you have for front one, you have low diffusion, but high global efficiency. And these are generally modular graphs. What modules means you have like different cores, okay? And here, these modules, like they're internally densely connected, but externally weakly connected. So these communities, within a community, you have a very good diffusion, but across communities, it's very low. So you cannot, and information cannot easily diffuse from here to there, okay? It's very weak. For that reason, globally, you have a very low diffusion, okay? So, great, so that's it. Now, the last part, if you remember, it's like this is the very last thing, and we're gonna wrap up in a minute. So communicability. So you guys now understand what is the morphospace? How can we explore graph structures? How can we evaluate? Now you can also, all the measures that we have seen in this class, you can also plot them. You can plot them in a high dimensional space and see where your point is, where your graph is on your space, to investigate its efficiency. Okay, like for example, what did we see today? What? Search information. What else? Anyone remembers? Search information. Come on, guys, you should remember. Yes? Sorry? Transitivity. Yeah? Anything else? Okay, so earlier we seen the average number of hops, okay, which we used to define what? The average number of hops, we used it to define the diffusion, okay? The efficiency of the diffusion. Now the last part is communicability. How we define this? So this is a measure of graph integration that is consistent with the diffusion model of information flow. So communicability, it accounts for the contribution of all possible walks between a pair of nodes. Okay, so we're looking not just at the shortest walk. We're not to find or focus on the shortest walk, but communication basically between two nodes. So we're looking at all possible walks, and this is from a random perspective. So we have a random walker, okay? So if A is a binary adjacency matrix, communicability between nodes I and J is defined as basically this. So we are just summing over the total number of walks between I and J comprising n edges. So this is exactly the adjacency matrix to the power of n. So this is the number of walks of, that have exactly n steps. And we're varying the n from 0 to infinity, okay? And then we're normalizing somehow by this weight. And this is, the factorial. So if you guys remember, this is exactly the definition of the exponential, right? So this is the Taylor expansion of exponential function, okay? So this is how it is defined. And here, if you have, this is the definition, n equals 0 to infinity of x to the power of n. So this is the Taylor expansion. And here we define communicability using this. So what does it mean? If we look at the communicability between I and J, it's the weighted sum of the total number of walks between a node pair, okay? Total number of walks of any length. So the length is the n, okay? And then we notice that longer walks, using this formula, longer walks, they contribute less to the sum, while direct connections contribute most. Why is that? Because we're weighting, right? So the longer the walk, it means the more steps I need to take. The more steps I need to take, the higher the n. The higher the n, the higher the n factorial. So we're down weighting longer walks in this one, okay? So we want to look on average that, okay, if these two nodes can communicate, let's give more weights to direct connections. So which means if node I and node J can directly communicate, well, their communication will be high. But this is most important because it's direct communication. But we can have a mediated communication via a very long path. I'm going to still count this one in my communicability measure, but I'm going to down tune this path, okay? Because it's longer. That's it. So here, let's look at this example. So we have a matrix A. We raise it to the power of 2, 3, and 4, which means, we can here like I navigate the graph like I navigate, or I go from node I to J in exactly 4 steps. So A to 3, let's look at this one, is equal to 0. We notice that it's equal to 0 when n is an odd number. So this node pair can only be connected with a walk that traverses what? An even or odd number of hops. You guys can choose even or odd. Let's read this and notice this. What is E23? Let's find it. 2 and 3. A23, sorry. Okay, this one. Okay. No. Am I right? To the power of n. Yeah, I'm right. So, what do you guys notice? So when n is equal to, here it's equal to 1, and then 2 and 3. So when it's like an odd number, it's set to 0. So what is the right answer? This node pair can only be connected within a walk. So we can only go from 2 to 3. I can only go from 2 to 3 if the walk has how many steps? An even number or an odd number? Even number, yes. You guys got it. Okay, so sometimes you just need to focus. So easy. Even number. Okay, so now let's look at the other one. A to 3. So we want to go from 2 to 3 in exactly 4 hops. So this one, okay, is equal to 2. Why is that? So I want you to find the walks. So it means that we have 2 walks between nodes 2 and 3. Can you tell me what these 2 walks are? And this is the graph. So I want to go from 2 to 3. So I can do this. 1, 2, 1, 2, 1, 3. Okay, so these are 4 hops. 2, 1, 2, hop. Or I can do the other way around. So, I can do, what is the other one? You guys tell me. 2, 1, 3, 1, 3. Okay? That's it. Cool. Now, what is the communicability between nodes 2 and 3? So it's very simple. So let's look at these two. So if we sum from n, from n hops and 0 hops to an infinite number of hops, we will get that this matrix, this these values will converge. The sum basically of this quantity, it will converge to 589. Okay, 589. Now, if we only take the first 4 terms, which means we stop at a number of hops equal to 4, what do you guys notice? That we get a very close number, 0.583. What kind of conclusion you can derive from this? So remember, this is our graph. And we want to go from 2 to 3. So these are very close. So what does this tell us about nodes 2 and 3? Communicability between them. So longer paths, what's happened to longer paths when n increases and, basically we increase it towards infinity? What's happening? Yeah, downrated because of the factorial, right? Very good. So yeah, so here, you guys can fill this in, it's easy. So you can read all the values from the matrices and add them up. So here, basically, the number of walks that traverse back and forth along the same edge, because we need to go back and forth if we have a larger number of, like when n increases. So yeah.
We could have like 24 different paths in the 4 hops, and that would make the communication value high, but there would be no like 1, 2, 3 hop connection between 2 nodes.
Okay, so what you're saying now, okay, so here we're discussing just this particular case, okay? Now, let me get your point. So what is the scenario you're illustrating?
There is no short connection between two nodes, but
okay.
There are lots of different paths.
Okay, so there is no short connection between our nodes I and J, but there are many long paths. Okay, so it means that, well, we're going to have many long paths. But these long paths are very time consuming, right? So even if you have communication, this is not regarded as good communication. So if you look at the many long paths that you need to spend energy to traverse to go from I to J, if you have one graph that have this, right? Or maybe just only two paths from I to J, this is actually, the communication is much better. So this is why we downrate with the factorial.
We couldn't distinguish between one another by just looking.
Yes, yeah, we couldn't. Good point. So yeah, right, so to generalize, one last thing, so to generalize communicability to weighted graphs, we just replace the adjacency matrix with its normalized version. So we have seen this, so this is a normalized version. And remember, the Laplacian is just, the normalized Laplacian is identity minus this quantity, okay? And here, this is, you know, what we call also the reduced adjacency matrix. And next one, what we need to do is simply plug it in. And this is the communicability we have for weighted graphs. Okay, so it's very simple. And generally, so this is something also to investigate, but I'm just saying this. I know that we haven't proven or demonstrated that, but communicability, basically, it reflects the graph capacity for parallel transfer, and it's under the diffusion model. Why we're using the diffusion model? Because remember, we're modeling this using random walker. We're talking about probabilities, and actually, this matrix is related to the probability of the random walker. Okay, cool, great. So that's it for today. Any questions? Okay, guys, you have so many cool things. I'm gonna send you this. Oh, this is a paper. I'll show you the paper. I started reading it. I thought about doing it here, but it's gonna take a lot of time. But it's a very nice paper with lots of videos. I really like this paper, and they profile all types of graphs. Yeah, and here they have like different fronts and different measures with different graph structures. So feel free to read the paper.